We're going over 6.5 proportionality theorems, especially those in triangles. All right, so the first theorem we got is theorem 6.4. It's called the triangle proportionality theorem. And it states if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. Basically means it cuts them in parts that are, if you compare the ratio between them, will be the same. So what we have here is that we have QS and TU are parallel. Now, again, TU does not necessarily mean it's a midsegment. It doesn't mean it goes to the midpoints. If it does, easy. It's a 1-to-1 ratio for the sides. The midsegment theorem follows this theorem. This theorem actually holds true for it. But this means anywhere. TU can be anywhere. It can be really close to QS, it can be closer to R. It doesn't matter. But if they are parallel, then if we're looking at QT compared to RT, so we're taking just that side RQ, QT to TR, RT is the same as US to RU. All right, so small piece to a bigger piece, and a small piece to a bigger piece. So again, QT to TR, US to UR. All right. And this will always hold true. So for example, if we had numbers such as if this was 2 and this was 10, then US could be 1 and UR would be 5. It doesn't necessarily mean the numbers, but what you see is that from QT to TR, it's 2 to 10, which is a 1 to 5 ratio. Same thing with SU and US, it's 1 to 5. So the ratios will hold true between them. The next theorem is theorem 6.5. It's the converse of what we just did, the converse of the triangle proportionality theorem. It says, given any line that divides two sides of a triangle proportionally, so basically TU is just dividing two sides proportionally, then it is parallel to the third side. So it kind of goes along proving a line parallel, is that if TU cuts QR and RS proportionally, then we can say TU is parallel to the third side, or QS. So we see here that QT is 2, TR is 4, SU is 3, and UR is 6. 2 to 4, 3 to 6. Both have that 1 to 2 ratio. So again, we go at RT is 4, TQ is 2, RU is 6, US is 3, and you see they're both 2 to 1. And again, if you do it upside the other way around, where you did TQ over RT, is US over RU, doesn't matter. They're all the same. They still will hold that 2 to 1 or 1 to 2 ratio, depending on how you're comparing. Once we have that, then we can tell us that TU and QS will be parallel at that point. So it's the converse. So it works both forwards and backwards, the triangle proportionality theorem. The third theorem we learned today is basically like one we've seen before, except we're not doing two parallel lines to the third line. We're basically going three parallel lines that intersect two transversals. So if three parallel lines intersect two transversals, then they divide the transversals proportionally. So those parts of the transversal they're cutting are proportional to each other. So we see that V, S, and T are parallel. They're cutting the lines L and M. And again, L and M not necessarily parallel. If they are, makes it a lot easier. But if they're not, it doesn't matter. It still works out. And we see that if we take the segments that are created, we have UW, WY, VX, and XZ. Those four segments are proportional to each other. So UW to WY is the same as VX to XZ. You could also go, if you really wanted to, you could go just the parts in between each parallel line, UW to VX or WY to XZ. You'll still hold the same properties. So do not worry about that. Either way it works, they will always be proportional. And then our fourth theorem, now this one's a little bit trickier to get through because it's not just parts, it's parts and sides. Theorem 6.7 says if a ray bisects an angle of a triangle, so we have an angle bisector and everything that entails. We bisect an angle. So here we have our thing CD is bisecting angle C. Then it divides the opposite side. So whatever side it's going through away from the angle it's bisecting, so in our case here, AB, it turns the lengths of those sides, the sections it is cutting, are proportional to the sides that are attached to them. So lengths proportional to the lengths of the other two sides. So what we see here is that CD bisects or is intersecting AB. And then AD compared to DB is the same as AC compared to CB or BC. So the two smaller segments to the two sides. And basically it's top to bottom, top to bottom. Segment on top, segment on bottom, side on top, side on bottom. And that's kind of the easy way. If you want to do left and right, depending on how it's drawn, works out the same way. All right, so let's look at a couple examples here. We're going to start with the one on the left. Just going to cover up the one on the right so we don't look at it yet. The one on the left, we have three parallel lines. Well, those three parallel lines, right, if we remember from our theorem previously, cuts the sides proportionally. So when we set this up, we can go, okay, we got our sides, we want to do our proportion. So proportionally, we can set it up as x to 120 is the same as 300 is to 150. And at this point, we need to solve for x. And to solve for x, what we're going to do is we're going to do how to solve proportion, which is cross multiply. Now, we know 300 and 150 are both divisible by 150, so we can actually reduce that. And what we end up with is x over 120 equals 2 over 1. And now we can cross multiply and we get x equals 240. And there's my answer. If you had decided to go x over 300 is equal to 120 over 150, that's fine as well. Because you'll notice that the x is still multiplying the 150 and the 300 is still multiplying the 120 just like it does in our original. So either way you set it up will work. You'll still get the same answer. So now you're doing 12 and 15, but you'll still get down to 240 in the end. All right, let's take a look at the next problem here. All right, so this time we have a triangle, QPS, and we have PR. Well, notice PR is a bisector of angle P, which means that since it's bisecting angle P, that where it intersects QS are proportional to each other. So we know that QR to RS is the same as QP is to PS. So I'm going to go ahead and write that as a proportion here. We know that QR over RS is the same as QP over SP. And now I'm just going to fill in my numbers here. Well, the easy one we know is QP is already 7. We know SP is 13. We know that RS is X, but what is QR? Well, if QS is 15 and RS is X, then QR has to be 15 minus X. So we need to put 15 minus X over here. And if you think about it, guys, if I told you X was 5, what would QR would be? You'd say 10 right off the bat. Well, how'd you get it? Well, you subtracted 5 from the 15. So there's where we get, we know it's X, you subtract X from the 15. And so that's where we get that one. So now we do what we've done before, solve a proportion, we're going to cross multiply. And so we get 13 times 15 minus X is equal to 7X. Distribute the 13, I'm going to get 195 minus 13X equals 7X. I'm going to add 13X to both sides. And I get 20X. I get 195 equals 20x. I'm going to divide both sides by 20. Now, with this, is we will notice, right, that 20, since x is now equal to 195 over 20, right, they're both divisible by 5. So if I cancel both of those by 5, I end up with 19 over 4. So in this case, x equals 19 over 4, and there's my answer. All right, so you just got to be careful with your solutions here. Oh, it's not 19, I'm sorry, 29. Sorry, 29. I'm sorry, I did that wrong. 29. No, wait a minute. I'm really messed up here. It is 39. 39 over 4. Yeah, 39 over 4. 5 goes into 195. It's basically like 240 times, which is, take 1 away, 39. 39 over 4. So my mistake on that, not 19, I meant 39. I was thinking 95. Sorry. 39 over 4. So That would be our answer. And if you put it as a decimal, it would be 9 3/4 or 9.75, which we don't really care. We just leave it as a fraction. So keep practicing these problems. Make sure you do your homework, and I will see you guys next class.